I'm Sven Stumm. I'm here representing the chair for Individualized Production and Architecture from the RWTH Aachen University, which is led by Sigrid Brell-Kotschan, who also is a co-founder for the Association for Robots and Architecture, together with Johannes Braumann, and I want to present a little bit about synthesis of human and robotic work, especially talking about human and robot collaboration and some experience we had with this topic, and what we kind of introduced as a form of haptic robot programming. So, this one actually doesn't work, okay. There are, while the Association for Robots and Architecture focus a lot on making robotics accessible for architects and artists and creating an easy way to program robotics, we also focus a lot on actual production processes, how to construct, assemble, and create architectural constructs, and we also want to focus on trying to shape the construction side of the future, where we see humans and robots working together in a very unstructured environment. So we mostly work with industrial robots, which are usually used in a very controlled environment. You have very specific positions, and you have a very static program how the robot should move. This is something you can also do if you work in other control spaces, like on a stage or something like that. And but we want to focus on very dynamic environments. We don't want to pre-place everything. We just want to enable people who have never worked with robots before to be able to work with them. There are a lot of robot programming paradigms and everything, but current robot programming, as I was shown by somebody, currently still looks a lot like Charlie Chaplin's Modern Times. You have a very static mechanical flow, and the human has to compensate for the motion that the robot does. He has to actually be able to compensate for the very static motions the machine does. The automaton just works by itself without respecting any requirements of the human worker. So we wanted to get away from this very static process, because it leads to, as you can see in the Charlie Chaplin movie, it leads to a lot of problems, because it won't stop at any point. It will just continue on working. Maybe for safety reasons it will stop, but usually you have to compensate for everything. So this can go horribly wrong, and it actually the design of industrial robotics is often very focused on the static movement, because they want to have predictability. That's very important, but it's contradictory to having autonomy in a machine. So we wanted to create kind of a middle ground between the very static and the very dynamic, which you can't predict in any way. So our work started, especially from the association, started with the Parametric robot control, which used parametric models of the environment. We can just change different parameters and directly see how it influences the robot's movement. This kind of allows for mass customization. So if you have any changes in your environment or in the parameters you want to work with, you can directly see if the robot is able to handle these changes. and directly move accordingly. This is very useful for fabrication processes where we want to create individual shapes, use maybe some sensor information, some video material to create kind of pattern and images and put them onto different surfaces, or create different kinds of shapes for creating architecture. So yeah, for this Red Bull arc, we, the association, worked together with some artists who also never programmed a robot before, and they kind of showed them if they use this kind of parametric model, they can create the different forms out of styrofoam and then just pour in the metal and create this shape. There were also still some problems with that because the material pulls together a little bit, so it shrinks. So that's something you have to think about. And what we often like to do is start very manually. So you need to get a feeling for the material you work with. So we do a lot of workshops where we work with students that actually try to design specific elements, and then we continue on in creating these shapes and structures with the support of robotics. So, we usually start out with a kind of form finding process. People trying to pull in, and then they try to design it, create a model for this environment, and then they continue on with the fabrication using robotics. The freedom of an industrial robot, the 6-degree freedom, allows it to create very dynamic shapes, and it's, as I said, it's very nice for fabrication, but we also wanted to work a little bit more in the assembly part. So, as part of the robotic woodcraft project, we kind of fabricated these wooden parts, and then the students, with a lot of hands, had to manually go there and assemble it, which was a very not so easy task. And we wanted to see, okay, how would a robot go into doing something like that? So we have different material tolerances. We work with natural wood, so every stick is bent a little bit, so we can't assume a perfect environment. We might not know exactly where the positions are, but we can still use a lot of the information we have from the design. So we don't have to go into it without having any knowledge of what we're working on. Because we designed it, we created a 3D model, we now should know what we want to create, and we want to teach that to the robot in an intuitive way. So actually we take the same positions we use for the process of creating the holes in the structure, and we use these positions to then define the assembly process. So there are different assembly tasks you usually work with when you're talking about assembly, but we just wanted to do first demonstration and show a little bit of the different tasks. So there's usually some kind of handling. You need to work with the material, transport it somewhere. You need to verify the material. So we use the internal force torque sensors to actually measure the length of every stick, and then we cut them down to size and started joining them. So before we put it onto the robot, we created a digital model, and we then let actually the visitors decide how the structure should be continued. So they parameterized the model without working in any CAD environment or anything. We just moved it onto the robotic platform, and we wanted to find a way to directly parameterize everything on site directly with a robot without going back to this whole simulation environment. Okay, so that's what the basic process looks like. It just needs a few positions, and then we actually got the visitors to lead the robot around, and that's the part we kind of call haptic programming. There are two sides to it. The one where we parameterize the model, and if you look closely, you can also see that he tries to pull on the robot too much at the end, and it kind of restricts his movement. So because it has a design model behind it, it knows where the constraint space lies. So it doesn't allow for him to pull it out of its working range or in an area where the positions aren't aligned with the actual motion. So from this lower motion, we extrapolate how the curves then should look like. And yeah, so in this video, which is also, you can also see online, we show the complete process, which we did as part of the KUKA Innovation Award, where we got the robot as a sponsorship. And yeah, we try to use the internal force torque sensors to work with it. So we created a kind of program where it uses just manual tools and works in a normal environment. That was the first project we did like this. In addition to the part where we parameterize the curve and give it more information for the model, it also can online be corrected in its movement. Meaning, if it doesn't find the assembly position because the stick is bent, or if it tries to search for the position, but if the searching takes too long, then it will ask for help. It indicates that visually by just by a light that goes on, and people then can go in there, have the robot, move it around, and it will adapt to it. This adaptation process will be extended further to use real reinforcement learning, but currently it's a very simple model it uses. We wanted to illustrate how it could work, and we are currently still extending upon this. Yeah, and after the project we did at the Hanover Fair, wrong title, but yeah, we did a project, two master students of ours. They designed some building elements that could be foldable and could also create a foldable structure. They created this kind of helping device to better get to know how to interweave the different materials. They mainly worked with bicycle spokes, because they also wanted to do a little bit in the area of recycling, and then they thought, okay, we use bicycle spokes, which also restricted kind of the size of each of the building blocks, so they had to create a very high number of these elements to create a kind of movable pavilion, which they could move around, and we presented at the Robodonian, the Robot Art Festival in Cologne. And the video shows a little bit how it was created. First purely manual, and you saw the first video, the first part where it showed a little bit, okay, how could the robot work with the material. We adapted the program just a little bit to fit to the smaller sticks, so we needed a little bit different gripper and everything, but basically we could use a similar process to create a program for it. But we wanted to increase a little bit the interaction people had with the program. So we kind of removed the searching for the positions and just showed how people could directly interact with the robot to find the positions. Yeah, so these building blocks are put together with a shrinking material which reacts to heat, and then it shrinks down, and then it glues the parts together. Yeah. So that was the master thesis I worked on, and then we moved on to the Robotonian Festival, where we actually had a lot of people there. Okay, so the video is. Oh, okay, so to show you that the resulting structure is also foldable, I'll just show this part shortly. Yeah, they put them together with a shrinking material. It's shown here, and then. So actually, it can be folded together very small and then extended into a whole pavilion. That's one of the arcs of the pavilion. Okay. Yeah, we also put it onto a mobile robot, and we kind of modified it a little bit so people could work with it directly. And we just used the same form they used for teaching themselves how to do the process, and then we use it with the robot. So you can move the robot around to show the position. You can actually, by pulling it in the opposite direction towards where it's going, you can say it should go back into the program, and it moves back to the position before that. And so you can actually go in and reprogram everything just by hands-on working with the robot, while simultaneously getting some visual indications via the light. So we also did the material handling manually, so we just give a spoke to the robot and then push it down a little bit, and then it takes the spoke and works with it. That worked quite well. We had very small children who were also able to work with the robot, and they actually showed their parents how it's done, how you can move the robot around, how you can teach it different positions, and how you can get it to assemble this kind of foldable elements. Yeah, so that's what it was at the Robotonian Festival. Here we have the different parts here. So this is the material handling. So I'm just teaching the kid how to kind of do it. It's always have to use two hands if you hand something over here, but it's just because you can create better pressure. And yeah, they really enjoyed working with the robot, and also the robot kind of teaches them at the same time how the process works. So if you have this form and you see where a stick goes, you realize how the weaving process works. So both the robot gets informed by the manual operator, as well as the operator gets informed on how the process flow works. So as soon as it doesn't find the position directly. It also indicates that it can be moved around, and then it, after it finds the assembly position, it then starts the assembly. Yeah. Oh, it's still in German. And you can also, as I said, you can also rewind the process in a way. So if you push it against it, it moves backwards to the previous position. And we want to extend upon these kind of haptic interaction primitives. So we have a range of them, so people pull or push on the robot to get different reactions from it. So you can work with it on site and fit it to your needs. Yeah, I think that's basically my presentation. We also do a lot of different projects with the whole fabrication and these processes, but I wanted to focus a little bit on the human-robot interaction and how it can work. Okay, thanks.
Thanks a lot. How much did you use Laban when you constructed these arms? The movement ideas of Laban, were they taught into the construction of these arms?
No. So I think the shape of the Laban motion is not similar to the robotic workspace environment.
Actually, there was an entire workshop for roboticists at the Robot Science and Systems Conference on Laban notation for industrial and manufacturing robots. So there are plenty of people working with it. I think it's something to look into.
Yeah, but I think the shape is a lot more round and less, hexagonal space. So it's less of the clipping of some of the work environment of the robot if you use this kind of notation.
I think if you would want to, you could probably adapt.
Yeah, you could. But it uses the base geometries, and I think you can do a lot more complex motions. It also, I thought we kind of saw in the presentation of the Laban motion that it shows, okay, you go from this sector to this position, but within robotics you have different ways of traversing between these positions.
In human bodies, you have it too.
Yeah.
You have
Yeah. So I'm not so familiar with the notation, but I don't know how it compensates for this transition, because here for dancing it also seems important. But here it's especially important because if you don't handle that, you will probably hit something. Or
but at the same time, you have this issue of the way the robot is moving generates a psychological impact on the person that is handling the robot. And that is something that the notations with the spline curves is not taking into account at all. So there might be something between those worlds that might be interesting.
yeah, definitely. I think with the interaction, we had some really nice reactions from different people who were really, sometimes lighting up when they just saw, okay, if I push it, it moves. It's not not so static. It was just standing around there, and when people were coming to it. And we also put the camera on top of it, and we had some really great video material of that, of people reacting to the robot, reacting to them. And it also made the impression of the robot having an actual face, because we had the camera there, it looked like it had the eyes, and then the arm was like a face.
Great. We will continue that during the panel discussion.